Okay. So the table that we put together, Sir Logan, we're talking lollipops, which are spheres. So we use the idea that volume is equal to 4/3 pi r cubed for a sphere, because 4/3 and pi don't ever change. If we were to write this as a direct variation, we would write, oh gosh, how did we do this? We jumped around through this a little bit, but we said that P is equal to K r cubed. And what P was going to be production cost, the cost of producing a lollipop, which increases as the volume increases, right? Okay. So then from that, we put together a table of values.
Eligibility for high school and middle school is also today. Check your grades, check your email, attend homework help if you're required to, so you can keep up all the good work you do in activities. Walk or bike is still going on, so if you do either one of those activities, get your card marked. If you need a card, stop on by the office and we'll give you one. Prizes will be awarded October 7th. High school, we still have waivers anytime you need one for this year. If you're interested in one or want to know more, please see Mrs. Sundberg or Ms. Kristen. High school, during lunch, if you're sitting down on the far end of the building enjoying your lunch, please remember to social distance. You guys get to take your masks off and eat, which is a good thing, but you also need to spread yourselves out a little bit further, okay?
You know where those photo books went?
Cross country's at 3, volleyball's at 4:30, and DBS is also today at 3. Lunch, beef burger on a bun, potato salad, and fruit. Please rise for the Pledge of Allegiance.
I pledge allegiance to the flag of the United States of America and to the republic for which it stands one nation under God.
Okay, so you guys have all the numbers, right?
Yes.
So you'll be able to tell me really fast. So when we cube the radius for these three, what is it?
2.744.
And
9.261. 21.952.
and then this became, the ratio of the radius was 2 to 1, 3 to 1, 4 to 1. And because it's a volume, it's cubed, it's in 3 directions, it's 3-dimensional. If you make it 3-dimensionally larger, you got to take length times width times height. And in this case, it's radius times radius times radius. So you got to cube that ratio. So 2 times 2 times 2 is 8 to 1. 3 times 3 times 3 is 27 to 1. 4 times 4 times 4 is 64 to 1. Therefore, the volume, the relative volume is 27 to 64 times as big. So our production cost goes from a half cent to 4 cents to 13.5 cents to 32 cents. Bingo. Got that done. So we did that, we talked about all that kind of stuff. And that goes all the way back to the Green Book with the mystery of Blacktail canyon. That's where that volume stuff was taught to you initially. Okay, then, remember, this is not your book, this is your book. Then I wanted you guys to go home and put together another table, right?
Yeah.
Is that right? And that has to do with fitting them into a carton. So if we're going to fit them into a carton, packaging in other words, or shipping carton, we need to come up with a size, the radius, the ratios, and the number of pops. So, you know what I want to, well, yeah, I'll just make a new one. So size. There's the mini, the regular, the jumbo, and the super. Okay, so the ratio of the volume to the mini volume, and then the number of pops per carton. Okay, so they said you can get 270 when you have 270 of the minis in there. So volume-wise, with the regulars, if they are 8 times as big, what fraction of 270 will you fit into the carton? If they're 8 times as big, how many will you fit in there? What fraction?
30, no.
An eighth, yeah, you're only gonna fit an eighth as many. Because their ratio is 8 to 1, so that means for every 8 of the minis, you can only fit 1 of the regulars in there. So now we gotta take 270 divided by 8, which is how much? I'm sorry?
33.
It's 33, comes out.
Not perfect, but.
There was a 0.75.
0.75,
Yeah, but you're supposed to.
supposed to round it off, so you're only gonna get 33 in there, and they're gonna rattle around and chip, and they're not gonna be as nice. Oh well, big deal. They're just lollipops. Jumbos are a 27 to 1 ratio, so you're only gonna fit a 27th, which is 10 of them. 27 over 10, over 270 over 27. And then we've got a 64 to 1, so we're only gonna fit a 64th. So, how many? You only fit 4 pops in. So, the number of pops per carton is gonna vary inversely. It's gonna vary inversely as the volume cubed, or the radius cubed. So this is what we're doing here, a direct variation. Over here, I think the number of pops per carton is gonna be equal to some constant multiplied or divided by the radius cubed. And the constant is gonna be 4/3 pi k. But because 4/3 pi is also a constant term all the way through this, we incorporate that 4/3 pi into the k value. That's what was done over here as well. So, let's see, I'm just looking at the variables that they want to use. If the number of pops in a carton varies inversely as r cubed, and r is multiplied by a number c, then the number of pops is divided by so the number of pops that you can put into a carton is going to be divided by what we did here, r cubed. It's going to be the volume portion of this that we divide by, because the volume's got to go into the box. So we think of division as something going into. And so there's almost a comparison in that respect. So what does this give us? This gives us what they call the fundamental theorem of variation. And the fundamental theorem of variation is essentially, so let's see, the number of pops per carton is equal to k over r cubed. The production cost is equal to k r cubed. These two forms of equations are part of what is called the fundamental theorem of variation. So we have direct and we have inverse variation. This is direct, this is inverse. So they write this, they say if y is equal to kx to the nth, that is y varies directly as x to the nth and x is multiplied by c, then y is multiplied by c to the nth. So what do they mean by that when they say that? So if we've got y is equal to k x to the nth, if we change x, if we change this number that's being multiplied by a factor of c, then, so, gosh, how do I, let's say you had a cube. Let's do it this way. If you had a cube and now you made the cube twice as big in each direction, the original equation here would be as such. It'd be kx to the third power to figure out the volume of the cube. So now we go and we make the cube longer, twice as long, and all of that. Twice as long, twice as tall, and then we go twice as deep. So now we do this, and we take our volume of 1 and we change it into a volume of 8 because we did it, we doubled the dimensions. So now this new cube here is going to be y equals k times, not x to the cube, because in this case here, this is a length x, and we changed it into 2 times x. So now x has to be written as such in parentheses, because the 2 is also going to have this exponent applied to it. It's important that we know that the 2 also gets taken to whatever this power is here, n. In this case, it's the third power. That's critical. That's what the fundamental theorem of variation says. So if we had another situation where we were making this 5 times as wide and tall and deep, then you'd have to have 5x in parentheses. 5 times whatever your original value was. And that's what we did here. When we looked at r, and we said, well, it can't be r to the first, it's r to the third power. We started with the radius, and we said, okay, well, the volume involves an r cubed. That cubed number shows up here. We don't ignore the cubing. We don't just say, well, the volume is now, twice as big, 3 times as big, 4 times as big. It's not. It's considerably more than that, because, see, this number right here, this 1.4, is like 2 multiplied by 0.7. And if I took that to the third power, that's what gave us this number here. So you're taking into account every step of the way when we work with multi-dimensions, multiplying a number by the change in dimension to that particular power. Same thing happened here. What happened here is that we changed the r value by, in this case here, that pop size being 1/8 as big. Well, that number there is what we used as the r cubed. But this here was that the radius is twice as big, so that's 2 times 2 times 2. So instead of just taking the radius and cubing it, we did twice the radius cubed, and that's where that 8 comes from. And here the 27 came from the 3 being cubed, because it's 3 times the radius. That's the fundamental theorem of variation. So for the 3 of you, do you remember the mystery of Blacktail Canyon? When the kid is standing inside of a cubic-shaped room in a cliff dwelling, you don't remember that at all? You don't remember it? Gosh, your brother remembers it to this day and talks about it. It's hilarious. You remember it? And the kid says, oh, wow, well, this room is this big. The room next to it, which is also a cube, is twice as big, therefore it must have twice the volume. No, it has twice times twice times twice. It has 8 times the volume. And we spent a week on that concept and that idea. But it was very concrete. We were looking at pictures and we were taking measurements from these pictures and things like that. So, this is a little more abstract and very theoretical, and then the actual equations are given as such. And then there's a proof. Thought we'd be done with proofs, huh? Yeah. So the way they lay out the proof of this, you know, I've explained it pretty well, but it's nice to be able to look at a proof. So y sub 1 is the original value before multiplying x by c. So we start out with y sub 1 as our original value, and that's going to be kx to the nth power. That's the definition of direct variation. And we can do the same thing with inverse variation. We can start out with y is equal to k over x to the nth, because that's what this one is based upon right here. So then they say, well, y sub 2 is going to be when x is multiplied by c. So to find y sub 2, we have to x has to be multiplied by c. So y sub 2 is going to be equal to k times cx, because it has to be multiplied before it gets taken to the power. That's order of operations. And that's by definition what we're looking for. So if y sub 2 is equal to k times cx to the nth, we can rewrite this as k times c to the nth, x to the nth. That's the power of a product. And then what they do is they go and they use the associative and the commutative properties and they move things around. And what they're doing is they're bringing c out front. So they say y sub 2 is equal to c sub n, c to the nth times k times x to the nth. And then what they do is they associate these two here, bring them together. Because then what we can do is we can say, well, what is this? That's this, right? So now y sub 2 is equal to c to the nth times y sub 1. And that's done by substitution. So what this does is it tells us that when we find an initial value here, such as this, that cube of the many, if we take c to the nth, the change in the dimension to the power that we're using, and the change in the dimension here is that it became twice as big. So if we take that c value and we take it to the third power, we get the number that we multiply this by to get to here, which is 8. And then when we made it 3 times as big, we have to take 3 to the third power, so that's 27 times as big. Please take time to understand that one. Even go back and look at this video again if you need to hear it or read it. Take this one to heart. This is really, really critical stuff in your math upbringing. And it may seem all real now, which is okay. We're starting to get into more challenging things. You want to ask anything? Don't ask me what I did this weekend.
What did you do this week?
Not much.
Did you use the quadratic formula?
Repeatedly used the quadratic formula. Yeah, winterizing motors and waiting for a bull to walk through the property. Middle of the night, waking up to hearing a cow in heat going, "Rah!" I was, oh shoot, it's the wrong time of day. Supposed to do that in the middle of the afternoon. So then there's a couple of examples that go into applying the thing. So this whole activity here was to get you to see step by step. Now, what we have to do is we have to be able to just take the fundamental theorem, find out what that C value is, stick it into the equation, take it to the nth power, do the work more efficiently, more quickly. So, Fruit Roll Industries, here we go, Mark Handy, needs a cost estimate for the wrappers of the new Super Jumbo Pop. Because the pop is roughly a sphere, the area of the wrapper is a multiple of the surface area of a sphere. Surface area of a sphere is 4 pi r squared. Can I erase this? You sure? Okay, 4 pi r squared. So that fundamental theorem that's in the book, you probably want to have that written down, but I'm not going to write it all up on the board. And it's on page 88. Just make sure you have that available to you. That's a serious study point. And if I was ever to give you a cheat sheet, like for the final or something, that would be a critical one to have. Do you want me to write it with you so you know how to put it into your notes? Yeah? Okay. We can write the whole thing word for word, but I'm not going to. I think you need to come up with ways to shorten some of this stuff. So it says, if y is equal to kx to the nth, and then it goes and it says y varies directly as x to the nth. So the next important part is, if x is multiplied by c, then y is multiplied by c to the n. So you might say, if c times x, then we have to write it like this. Y is equal to k cx to the nth power. So if you start with this, and c gets multiplied by x, then you have that. Same with inverse. That's a good way to look at it. This is that's your cheats for this set of 3 lessons. Okay, so the surface area thing here. So this is so we have this surface area is 4 pi r squared. So the cost W, does it vary directly or does it vary inversely? Directly. So we can rewrite this as the cost of the wrapper, which is surface area, is going to be 4 pi r squared, but that is going to be, I'm sorry, I want to write that as k r squared. That's what we need. I need k. Why can't I got it. That's a better place to do this. So it's going to be k r squared. And that 4 pi is going to be involved in the k. So if the cost varies directly, and they know that the wrappers for the minis cost 1.5 cents each, how much do the wrappers of the super jumbo cost? So W of the mini is equal to 1.5 cents. Now, the mini has a radius of 0.343, is that right? What's the mini's radius?
0.7.
Or 0.7, okay, yeah. So here we say now, 1.5 cents is gonna be equal to K times 0.7 squared. So to go from the mini to the jumbo, what do you multiply that by?
64. No.
That's volume. So the wrapper for the jumbo
2.1.
has to be K times, so now it's gonna be C,
Oh,
the change. So it's gonna be like C times 0.7 squared. And that C is how much? 4 times as big, isn't it? It's 4 times the radius times 0.7 squared. So that means it's K times,
Are we talking about the jumbo or the super jumbo?
what,
Just the jumbo is.
oh, they want the super jumbo.
Okay.
So they want the super jumbo. Is this correct for super?
yes.
It is, okay, good. So now we're gonna take 2.8 and we're gonna square it. But if we take a look right here, and let me back up. I don't want to write this. I want to write it like this. K is going to be equal to 4 squared times 0.7 squared. So what is 4 squared? 16. So now, on the right-hand side of our equation, we just made it 16 times larger. Let me slow down, back up. So by rewriting this for the super, we essentially took the initial equation here, and we made the right-hand side of that equation 16 times larger. So in order to keep things equal, what do we have to do to the other side of the equation?
Multiply it by 16.
We need to multiply it by 16. So if this is the initial equation here, 1.5 cents is equal to K times 0.7 squared, we multiply that side by 16. To get the super, we have to take this times 16. So 16 times 1.5 becomes 24. So this has got to be 16 multiplied by the mini price, which is 16 times 1.5 cents. So that's 24 cents. So the wrapper for the super jumbo costs 24 cents to produce, if there's no other variables at play here. So it's going to cost 16 times as much. Now, when they work this out in the book, they do it a little bit different. You know, they say, well, this right here is the wrapper cost of the mini, and then they pull in that 16. I took more steps to get the 16 there for you, so you can think it through. You can get there as quickly as you want to with your work. But I think all you're really doing is you're looking for that C value. That's the important thing. And you're taking both sides of the equation and you're multiplying them by C. Because in the proof, for example, we have y sub 1 and y sub 2. The first instance and then the changed instance is y sub 2. And y sub 1 times c is equal to y sub 2 by proof. Okay, the weight of a land animal of a particular type varies directly with the cube of its femur diameter. The weight varies directly with the femur diameter. Does it say cubed? Yeah, the weight of a land animal of a particular type varies directly with the cube of its femur diameter. So, Fulberomys, an extinct rodent that lived over 5 million years ago, is an ancestor of the modern guinea pig. Its femur diameter is 18 times that of today's average guinea pig. Estimate how the weight of this rodent compares to the weight of a modern guinea pig. So, the weight of a guinea pig is equal to kf cubed, a particular femur of that guinea pig. All we have to do here is say, well, the weight of, however you say that, Fulberomys is now going to be equal to that femur, but it's how many times the diameter?
18.
18. So it's going to be K times 18F, because we have 18 times the femur diameter to the third power. So the difference between these two is 18 cubed. So the weight is going to be 18 cubed times the weight of the guinea pig. So it's a big number, isn't it? I don't even know what it is. The book, I don't know if they figure it out. 5,800 times. So this is going to be 5,800 times. And all we're doing here is we're looking at what we're multiplying the factor that gets cubed by. And we're cubing again that particular multiple. So, you know, if you have something that says y equals kx to the fourth, and you're saying that x is going to be multiplied by 3, so then what you're going to be doing is you're going to just be saying that 3 times x has got to be taken to the fourth power. So the end result is going to be 81 times as big. So that change factor of what's being taken to the nth power has to also be taken to the nth power. Indirect and indirect. So setting these things up is what the work is all about. Any questions on that?